Assalamualaikum warahmatullahi wabarakatuh. My name is Dini Zulaikha binti Mohammad Shokri, and I will be presenting the introduction, problem background, objective, scope, and conclusion. First up is the introduction. So mushrooms are edible fungi that could provide several beneficial nutrients, including selenium, potassium, fibroflavin, niacin, vitamin D, proteins, and fiber. An American Journal of Botany indicated that there could be more than 5 million species of mushroom. Because of the increasing awareness regarding the nutritional benefits and affordable prices, this has driven the growth of the mushroom market and making them in high demand. Next is problem background. It's important to differentiate between edible and poisonous mushroom, as there is no single trait that is exclusive to toxic mushroom. So in this experiment, we want to make the system learn to recognize types of mushroom and identify if it's an edible species or a poisonous species. Next is the objectives. There are three objectives of this study. The first objective is to be able to differentiate between edible and poisonous mushrooms. The second one is to be able to pre-process the mushroom data so that it is suitable for training. The third objective is to achieve a high accuracy with a small number of epochs. So now we move on to scope. So this data includes description of hypothetical samples corresponding to 22 species of mushrooms. The data included 8,124 observational rows and 22 categorical feature columns. So out of 8,124 rows, 4,208 are classified as edible and 3,916 were poisonous species of mushroom. The total number of training data is 6,499, while the testing data is 1,625.
Hello, hi, I'm Mohammad Hakim bin Abdul Halim. So for today's presentation, I'll be presenting the demo of our program, Artificial Neural Network Architecture, and the experiments we carry out to achieve best accuracy for this classification model sampling. So I'll begin by presenting the demo of our program. Firstly, we're importing the libraries such as NumPy, Pandas, Seaborn, TensorFlow, and Matplotlib as well. So we're just gonna run this. This star here shows that it is still running. Alright. So next, we're importing we're gonna load our data set using pandas.read.csv, and we're gonna paste the file paths of the data set on my Mac. So we're gonna run that, and there it goes. So we have 23 different columns, which the first column class here represent the output, and other 22 columns refers to our variables or features that affect the classification of mushroom. So, but we can see here that the data is in text level, not numerical level. So we're going to convert those using the sklearn pre-processing import level encoder that we have already declared at the beginning. We're going to use sns.countplot to visually show the amount of each class in our data set. And from here, we can see that our data is pretty balanced for edible class and poisonous class. So next, we're going to pre-process our data. So here, we're going to encode all of these labels into a numerical format so that we can feed it into our models. So mappings equals to empty list, and basically we're just going to fill that with all of the dictionaries for each feature. We're going to convert every unique value in a given feature to be its own numerical label. And then we're going to create a dictionary that maps those numeric labels to the text labels. So in order to that, we need our encoder, which is just a label encoder object, and then for column, in the range of data column, we're going to set the column equal to its newly encoded version. So data.columns, subcolumn, this will be written the data column, and this will take the slice of that data set, of the total data set for that given, I would say what? For that given column name. So we're going to set that equal to encoder.feed, which is going to transform to update those values in making them numerical labels. Then we're going to append to our empty list a dictionary of mappings for that specific column. So we call it mappings dictionary, and that's going to be the dictionary mapping and index to a label. So when we do mappings here, it will show the dictionary provides the mappings for every unique value in that column to its corresponding numeric value. As you can see here, adab class is set to 0, importance class is set to 1, and same goes to the other features. So next, we're going to split our data into X and Y. So in this Y class column, which we're trying to predict whether it's edible or poisonous. And X is other than that. So we means that X refers to the variables, the features. So X, so we're going to drop the class column for X. So now we can see that the Y is going to be a vector of our classifications, and X will be our original data set except without the class. All right, it begins with the cap shade and continue with the other features. So next, let's split our data with string test split function. So xstring, xtest this will give us 4 different slices of our data set. Y train, Y test is equal to train test split, X, Y, and we will specify the train size to be 80%. Since we have a decent size with 8,000 samples, this test set will be large enough to give us accurate accuracy. Next, we're going to explore our data. We can see that here shows 6,499 data. We will be used for training, and we can see here that 1,625 will be used for testing. So this is this plot histogram is to visualize the number of training and testing data, and same goes for this. Just to visualize each numeric input variables of 22 features. Yeah, let's see that the histogram for every features. So we proceed to the next that is important, which is we're going to proceed with building the model. So first, in Keras, we can build a sequential model. Keras defines the sequential model as a linear stack of layers. This sequential model will be Keras implementation of an artificial neural network. We already import sequential from Keras models and dance and activation from Keras layers in the beginning just now. Next is creating a variable called model and set it equal to an instance of a sequential object. These dance are actually refers to the layers. Dance is the most basic type of layer within a neural network, and it connects each input to each output within the layer. The hidden layer would be considered as dense layer because it's connecting all of its inputs to each output node within the layer. Here we have our model object set to an instance of sequential that's taken an array of 2 dense layers, and within our dense layer, the first parameter that we're specifying, which is 50 in our first layer, is the number of nodes or neurons within our layer. And the second parameter, input shape here, is going to be the shape of our data that we're passing into our model, which is input dimension of 22. And the activation function is typically a nonlinear function that follows a dense layer. So as you can see here, we are using sigmod. Alright, because sigma activation function, we can see here that which is good in the handling the prediction problem. After the layer is ready, we compile the model. So in order for us to use the model, we need to compile it first. Before the model is ready for training, we need to set up more things. We're going to set the loss function, optimizer, and metrics that we want to use. So I'll just run this. Yeah. Right, next is train the model. To start the training, we call the model.fit function. So we're going to set it to 50 epochs. And I already ran this to save time. So as we can see here, the accuracy reached to 100%. So as we can see here, at the first 3 epochs, it already have good accuracy. So it means that this model have very good accuracy. But this is a training accuracy. As the model trains, loss and accuracy are displayed, and this model reaches an accuracy of 100% of training data. Then we're going to evaluate the accuracy. We want to compare how the model performs on the test data set. Now we want to evaluate our data with our test data of 1625 that the fit model hasn't seen yet. We want to see if the fit model is able to evaluate the test data correctly, and we can see that our model is more capable of classifying the problem that we want to address. So from the 1625 test data, it have the test accuracy of 100%. This equal number of training and testing accuracy shows that the model is good. No, means there is no underfitting or overfitting occur. Then we want to see the training and validation loss graph. So this I'm going to explain later. So basically, just going to run it, and then we're going to make a prediction. So we want to predict our test data. So I'm going to set y predict with the condition of class 0 and 1. So we're going to see here, I ran a 20 random y tests here. And when I run y prediction, it shows the class of the prediction. So we're going to see whether it's true or not. We can see from here that the prediction is the same class as the test data. All right, here is 0, and for the y test original is 0, 2, and for the prediction continue with 1, 2, 3, 4, 1, and same goes with the y test. Then we would like to verify our predictions by classification report to show the accuracy of our y test and y prediction. So it shows a 100% of accuracy. We also can visualize our prediction and the test data, whether it have an error or not, by using the confusion matrix. As you can see here, we have 850 edible mushrooms correctly identified as edible mushroom. 0 is incorrectly identified as poisonous. And 775 out of 775 poisonous mushrooms are correctly identified, and 0 poisonous are incorrectly identified as edible. So this shows that all mushrooms are correctly matched to their classes, either edible or poisonous. Then we would want to use our train model to see whether it's correctly done. So what class of mushroom would it be? Then the cap shape we were going to set to 0, and the cap color also equals to 0. So as we're going to see here, when the cap shape is 0 and the cap color is 0, it's classified the mushroom into class 1, which is poisonous. So we cannot eat the mushroom. This shows that our model is correctly trained. So it's a very good model, and a big thanks to my group mate Dini and Aqizah, as we together working so hard in making this model to reach its best accuracy. So proceed with the presentation. So yeah, here the network structure was found on a trial and error basis, as we make a lot of experiments to find the best accuracy. So in the end, the best results are obtained for a network with the following structure, which is 22 input neurons in the input layer, one hidden layer with 50 neurons, and an output layer with 1 neuron. So the summary of this model includes information about the layers, the output shape, and number of parameters in each layer, with the total number of parameters in the model. At the bottom of the summary, the total number of learnable parameters within the network, which is 1,201, are displayed. That Keras refers to as trainable parameters. Yeah. So first, we're going to see on number of hidden layers. These 3 experiments involve changes in number of hidden layers, with other hyperparameters remaining constant. So the first experiment is conducted with 3 hidden layers of 150 times 100 times 50 neurons. And the second experiment is conducted with 2 hidden layers of 100 times 50 neurons, while the third experiment is conducted with 1 hidden layer of 50 neurons. So the idea of reducing the number of hidden layers is to keep the neural network as simple as possible. And the results from the experiment shows that the best accuracy is 7.97%, comes with one hidden layer of 50 neurons. Means that when we decrease the number of hidden layer for this sampling, it shows better accuracy. And then this next trio experiment involves changing the number of batch size. So previous experiments are conducted using a batch size of 256. Batch size refers to the number of samples from the training data set used in the estimating of the error gradient. So the batch size may influence the speed for the model to learn and stabilize the learning process. And from here, the best number of batch size is 32, as it has the greatest accuracy from these experiments. And proceed to the experiment of optimizer. So from here, we can see that Adam optimizer provide better accuracy value for the sampling with 96.43%. So we can see here that the accuracy jump up to 12.65% from the previous test, the experiment 7, which is using the SGD optimizer. So this shows that optimizer Adam suits our model well. And the last experiment is on number of epochs. So number of epochs is a hyperparameter that represents the number of times we want the algorithm to train on the whole data set. So based on the experiment above, increasing the number of epochs to 50 produce maximum accuracy for this sampling, which is 100%. So this experiment shows that when the number of epoch increases, the accuracy of the sampling will also increase. So as we can see here, we can conclude that the best neural network consists of one hidden layer containing 50 neurons. Using the Adam optimizer, 32 batch size, 50 epochs and other hyperparameters remain constant, will produce 100% accuracy for this. So as you can see, on this loss, training and validation loss graph, the gap between the training and validation curve on 50 epoch is minimal. So this means that the graph of training and validation loss shows a good fit.
Hi and Assalamualaikum to Sir Mohammad Razif and to all of my friends. My name is Aqizah Binti Amran, and for now I want to present about the result for our experiment. In terms of response time, we use Anaconda Jupyter to train and test the dataset, and the time taken to validate the training data takes up to 28.6 models. And this model achieved a maximum accuracy of 100% for classification and of edible and poisonous mushrooms. From this experiment, it indicates that only a short time is needed for training the model to achieve the maximum accuracy. Next, in terms of hidden layer. In terms of hidden layer, the best network after several experiments is a network with one hidden layer with 50 neurons. It is because it able to give accuracy up to 77.97%, which is 6.03% higher than the other experiment that used two hidden layer, and 45.13% higher than experiment that using three hidden layers. For the two hidden layer, the accuracy is 73.54%, and for three hidden layer, the accuracy reached only 53.72%, which is lower. So the idea of reducing the number of hidden layer is to keep the neural network as simple as possible, and this experiment shows that the accuracy of the sampling will be increased when the number of hidden layer is reduced. Next, for the number of batch size, we use 32 number of batch size for this experiment. It can reach 85.6% of accuracy, which is higher than the other experiment that we use more than 32 number of batch size, which is 128 and 64 batch size. Based on this experiment, we can show that the accuracy of this sampling will be increased when the number batch size is reduced. Next, for the optimizer. We use Adam as our optimizer in the experiment. Adam optimization is a stochastic gradient descent method that is based on adaptive estimation of first order and second order moments. It can reach accuracy of 96.43%, which is higher than the SGD optimizer that gave only 85.6% of accuracy. So we can found that Adam optimizer is suits well in our experiment rather than SGD optimizer. For the last, we in terms of number of epoch, the best number of epoch in training the model is 50, because at 50 epochs the accuracy already reached a maximum accuracy of 100%. At 20 epochs, we found that the accuracy already reached 99.57%. When we increase the number of epoch, the accuracy of the sampling also will be increased. Next, for the advantages and trade-off. There are significant advantages that can be seen throughout this classification study. As we know, the mushroom classification model is used to run on data attempting to classify the mushroom as poisonous or edible. It may help to reduce the number of ill people who are at risk of toxic mushroom. It can help by classifying the edible and poisonous mushroom on the basis of its feature. Next, the dataset comprises 22 numbers of nominal features. When the number of features and nominal attribute is high, it will provide the better accuracy for the dataset. So for our experiment, we have 22 numbers of nominal features that can give approximately 100% accuracy for dataset. Lastly, the mushroom dataset was distributed into two different classes, which are class 0, that refers to edible, and class 1 that refers to poison. Class 0 have a 4,208 instances, and class 1 have 3,916 instances. It can be inferred that the dataset is balanced because we have nearly equal amounts of data in every class, which are 51.80% for edible class and 48.20% for the poisonous class. From this, it indicates that the better accuracy can be achieved with this nearly balanced dataset. So we can say that our dataset is balanced. That's all from me. Thank you.
Now I will present the conclusion of this study. One output neuron indicates binary, which is either class 0, which is for edible, or class 1, which is for poisonous mushrooms. The average predictability rate is 100% for prediction of whether the mushroom is edible or poisonous. This enables people to classify whether their mushrooms are edible or poisonous. We can conclude that hyperparameters such as batch size, optimizer, number of epochs, and number of hidden layers could greatly affect the accuracy of the sampling. Dropout may be added in future works to eliminate other features that are less important in the classification of mushrooms. Thank you.